Hello everybody, welcome back to the Gregorius Maths video. In today's video, we are pressing on with the Advent calendar, as per usual. And yeah, today I'm going to be using Fourier series, more specifically Parseval's theorem, in order to show the following, that the sum from n equals 1 to infinity of 1 over n to the power 4 is equal to pi to the power 4 over 90. And yeah, we're going to be doing this with Fourier series. Okay, let's just crack on. So, firstly, I should state Parseval's theorem since we're going to be using it. So, Parseval's theorem says if you write out a function, f of x, as a0 plus the sum from n equals 1 to infinity of an cos nx plus the sum, plus bn sine nx. I might as well put it all into one sum, like so. So you expand it as a Fourier series, so you write it in terms of trig functions. Then we have that the integral from minus pi to pi of f of x all squared dx is equal to 2 pi a0 squared plus pi times the sum from n equals 1 to infinity of an squared plus bn squared. Like so. Okay, so this is what Parseval's theorem is telling us. So how on earth are we going to use this to our advantage, you may ask? Well, we're going to somewhat artificially write a function as a Fourier series, and this function that I'm referring to is we're going to look at the function f of x equals pi squared minus x squared, which you might be wondering, well, okay, this isn't periodic, so what are you talking about? Well, we'll just consider it on the interval between minus pi and pi. So the Fourier series that we're getting is, for the function that looks exactly like this, but it just is periodic instead of oh, sorry, I'm doing a smiley face and it should be a sad face. Instead of just going all the way down, it just goes boop, boop. Okay, you get what I'm saying. Anyway, so between minus pi and pi, and the first thing that we should see here is that this is an even function, so we're not going to get any contribution from the signs. Otherwise, this series wouldn't make sense. So we can just write it as a cosine Fourier series. And the formula that I'm using for the coefficients here is that an is given by 1 over pi times the integral from minus pi to pi of f of x, which is this guy, so pi squared minus x squared, times by cosine of nx, like so, dx. Now, the integral of cosine nx from minus pi to pi is just 0. So really what we just need to consider here is just 1 over pi minus 1 over pi times the integral from minus pi to pi of x squared cosine of nx dx. And well, sort of the obvious candidate for what to do here turns out to be the right one, so we just do integration by parts. So we'll use, thanks to black pen red pen for enlightening me with the DI method. So we'll use the DI method. So of course we'll differentiate x squared, 2x, 2, and we'll integrate cosine of nx to get what? Well, like 1 over n sine nx, and then we get minus 1 over n squared cosine nx. So this is equal to, so what, we times along the diagonals, so we get x squared over n sine nx minus minus is a plus 1 over n squared, I'll just write 2x over n squared times by cosine of nx evaluated at minus pi, at x equals minus pi and pi, and then minus plus, so minus. Oh, sorry, I should not forget about the factor of 1 over pi, minus 1 over pi at the start. So I'm just going to add 2 over pi times the integral. I'll take the n squared out as well, so n squared times the integral from minus pi to pi of cosine of nx dx. Now, we said before this just dies, so we can cancel that. And what are we left with here? Well, okay, let's consider this. So this guy here, well, sine of n pi, where n is an integer, is always 0, so we can kill this guy as well. And what are we left with now? So we get cosine. Okay, let's think about this for a second. Let's not make any errors. So, what do we have? We have cosine of n pi minus. Hold on. I'm getting confused with the signs. So I need to, okay, I need to write this out actually. So we get minus 1 over pi times by 2 pi over n squared cosine of n pi minus pi, so plus 2 pi over n squared cosine of, and minus n pi is just n pi. Like so. Now, cosine of n pi is 1 when n is even, and minus 1 when n is odd. So we can just write it as minus 1 to the n, basically. So we get a factor of minus 1 times by minus 1 to the n. That's minus 1 to the n plus 1 times by, and then when you add these two things together, you get 4 pi over n squared, but then you have to divide by pi, so you get 4 over n squared, like that. So, those are the a-n terms, and of course we need to deal with a0 separately. Hopefully you followed what I was saying. I was sort of working out the algebra as I was going along, so apologies if that wasn't clear. But hopefully if you stare at this long enough, you can convince yourself that this is indeed correct. Anyway, we need to deal with a0 separately. So a0 is just given by 1 over 2 pi times the integral from minus pi to pi of f of x, which is pi squared minus x squared dx, which is equal to 1 over 2 pi times by pi squared x minus x cubed over 3 evaluated at minus pi and pi. Okay, let me not make any mistakes here. Okay, so this is equal to 1 over 2 pi times by, what do we get? So let's just plug this in. So we get pi squared times pi, which is pi cubed, minus pi cubed over 3. So 2 pi cubed over 3. And then you plug in minus pi, you get minus pi cubed, minus pi cubed over, plus pi cubed over 3. Oh gosh, I'm confusing myself. Okay, let me just write this out. Minus, okay, and then brackets, minus pi cubed, minus is a plus, so plus pi cubed over 3. This is just minus 2 pi cubed over 3. Minus is plus, so we get 4 pi cubed over 3. Cancel the 2 with the 4, you get, okay, this is equal to 2 pi squared over 3. I believe. Yeah, okay, that seems good. Okay, so this is a0. So, what have we actually done? Okay, let me hope that okay, so we said f of x can be written as a Fourier series, and we've figured out the coefficients of that Fourier series. So now we have f of x is 2 pi squared over 3 plus the sum from n equals 1 to infinity of 4 times by minus 1 to the n plus 1 over n squared cosine of nx, like so. Okay, now the reason why this is good, and the reason why we chose this function, even though it seems artificial at first, is, well, now we have an n squared on the bottom. And that's really good because when we apply Parseval's theorem, we have to square the coefficients. So when we square this guy, we're going to get some constant over n to the fourth. So that's really good. So, okay, enough yapping about why this is really good. Let's just get on with it, you know what I mean? So, you know what I mean. So, what do we have? We have the integral from minus pi to pi of f of x squared, which is pi squared minus x squared and dx, is equal to a0, 2 pi times by a0 squared, I believe. Yeah, 2 pi times by a0 squared. So 2 pi times by 2 pi squared over 3 squared, plus the sum, plus pi times the sum from n equals 1 to infinity of 4 times y minus 1 to the n plus 1 all over n squared. Now, this side here, we can expand the integral to be the integral from minus pi to pi of pi to the fourth minus 2 pi squared x squared plus x to the fourth dx. And this guy right here is what? He is 2 times 4, so 8 pi to the fifth over 9. Yeah. Plus this guy here, well, the minus 1 when you square it is always positive. 4 when you square it is 16, so take that out. 16 pi times by the sum from n equals 1 to infinity of 1 over n to the fourth. Okay, good. This is good. This is a matter of just finishing the job, really. So this implies that, well, okay, let's just do this. So pi to the fourth x, sorry, let me lock in for a second here, minus 2 pi squared x cubed over 3 plus x to the fifth over 5 evaluated at minus pi and pi is equal to this side right here. Now, okay, what do we have here? So this implies that, well, let's plug this in. So we get pi to the fifth minus 2 pi to the fifth over 3 plus pi to the fifth over 5 minus pi to the minus pi to the fifth. No, minus pi to the fifth plus pi to the fifth. Plug in minus here again, you get plus 2 pi to the fifth. Oh, no. We've got 3 minuses. So we get, minus 2 pi to the fifth over 3, right? Because we're minusing everything here. So we do minus, which is plus, and then we plug in the minus pi, which gives you a minus overall. And then we already have a minus, so we have to add pi to the fifth over 5 equals this side here, which we'll deal with in a sec. Now, what is this side? Okay, so this is... I probably should have learnt the answer, so I don't have to figure this out now, but oh well. So we get 2 pi to the fifth minus 4/3, that gives me 2/3 pi to the fifth. 2 pi to the fifth over 3 plus 2 pi to the fifth over 5, which is equal to 10 plus 6, 16 pi to the fifth over 5, and that's equal to 8 pi to the fifth over 9 plus 16 pi times by, I'm just going to call it zeta of 4 so that I don't have to write the whole thing. Zeta of 4, This implies now that did we get 6? Oh, sorry, over 15. Yeah, over 15. This implies now that 16 pi to the 5th over 15 minus 8 pi to the 5th over 9 is equal to 16 pi times by zeta of 4. Now, okay, what does this mean? Well, what is 16 over 15 minus 8 over 9? Well, times this by 3, you get 48. Times this by 5, you get 40. 48 minus 40 is 8. This implies that 8 over 45 pi to the 5th is equal to 16 pi zeta of 4. Divide both sides by 16 pi, and indeed, thank goodness there's no errors. You do indeed get that 1 over 90 pi to the 4 is equal to zeta of 4. Boom. Yeah, there you go. Hopefully you gained entertainment from watching me fumble over the arithmetic and a little bit of algebra, some minus signs and stuff. It's a miracle this is my first take. It's a miracle I got everything first try. But yeah, hopefully you haven't seen this way of evaluating it. Hopefully you found it interesting. And if you wish, you can try generalizing this to find zeta of 2k. Because I believe this approach can be generalized. So, if you choose to try generalize it, have fun. If not, I hope you enjoyed the video regardless. And yeah, I'll see you tomorrow. So, goodbye.